Hi there, welcome to the second part of our multivariate regression analysis discussion. This video looks at two main areas. Firstly, the key assumptions that go into a multivariate regression analysis. They get quite technical, so I'm not going to go into them in too much depth. The second element is the problems that you may observe when undertaking a regression analysis and how to fix those problems. So this is a bit more practical. I think it's also helpful to have these in your back pocket in case you're criticizing someone else's work. So there are a number of so-called classical assumptions that must be met in order for OLS, ordinary least squares estimators, to be the best available. We're going to take them one by one. So the first is that the regression model is linear in the coefficients, is correctly specified, well that's assumed, and has an additive error term. So the key word here really is linear. A linear relationship is where there's, roughly speaking, a straight line between the two variables. A non-linear relationship is where there's some other functional form. So this could be exponential. For example, during the coronavirus outbreak, I'm sure we've all learned a lot about exponential growth functions. Exponential functions can shoot off very quickly into the stratosphere. Exponential functions are often used in the healthcare field as well as some other areas. In many social sciences, we're also interested in kind of U-shaped curves because sometimes functions might increase up to a certain point and then hit a limit and then go down. You also see this a lot in nature with growth patterns. For example, the health or the productivity of a particular plant might increase under certain conditions until it reaches a limit or a tipping point after which that function decreases. Now, all of these things can be represented in a linear sense if we kind of mathematically transform the variables. For example, using a logarithmic form to kind of counteract the exponential form or vice versa. And for a U-shaped curve, whether up or down, we might use squared values. If you have any questions about those kind of functions, if you fear you have them in your data set, then please let me know and we can work on those. A second assumption is that the error term has a zero population mean. And this is basically a core assumption, that the idea that each observation of the error term should be drawn randomly. And usually we assume this is the case, especially as long as all the other classical assumptions are met. Now this is a really important one. All explanatory variables are uncorrelated with the error term. It is assumed that the observed values of the explanatory variables are determined independently of the values of the error term. If an explanatory variable and the error term were instead correlated with each other in some way, there could be introduced bias into the OLS estimators. They would be likely to attribute to the X some of the variation in Y that actually instead came from the error term. So if the error term and the X were positively correlated, then the estimated coefficient would likely be higher than it would have been otherwise. And that's potentially a problem, especially if you're doing precise calculations. Another important assumption is that the observations, the error term, are uncorrelated with one another. This is commonly known as no serial correlation. If there is a systematic correlation between one observation of the error term and another, in other words, the individual observations of the error term are somehow in a pattern, as you can see in these charts here. If that were the case, then it would be more difficult for the ordinary least squares approach to get a precise estimate of each coefficient. So for example, if the fact that the error term from one observation is positive increases the probability that the error term from another observation is also positive, then the two observations of the error term are positively correlated. And this would violate that core assumption. I would say this is most important when addressing any time series data. I generally recommend that you don't use time series data. However, if you want to go ahead and do that, then make sure you include a time variable to try and correct for some of this issue. And we can by all means go over how you do that. It's relatively straightforward. Another error term assumption is that the error term has constant variance, i.e. no heteroscedasticity. Such a great word. The variance or dispersion of the distribution from which the observation of the error term are drawn are constant, is the assumption. The variance or dispersion of the distribution from which the observations of the error term are drawn is constant. That's our assumption. Here you can see a chart of what heteroscedasticity looks like. You have a kind of trumpeting effect such that the error term variance is increasing as the lots are drawn. A sixth assumption is that no explanatory variable is a perfectly linear function of any other explanatory variable, i.e. there's no perfect collinearity. Perfect collinearity between two independent variables implies that they are really the same variable. Or maybe that one is a multiple of the other, and or that a constant has been added to one of the variables. Now this is important because it can really influence the coefficient estimates. We test this first through the correlation matrix. That's why we include it in our papers. We can then run more meaningful statistical analyses if we think there's issues. The seventh and final assumption is that the error term is normally distributed. I hope that you're aware of the normal distribution concept. Now, it's important to note that this isn't absolutely required for OLS estimation. So now let's look at some of the common problems that we might experience in a multivariate regression environment. One of the most major problems is that of omitted variable bias. That basically means that you've not included a variable that is very important in your analysis. Not including a variable might bias the coefficient estimates. An example of omitted variable bias was shown in our last video. So how can this be detected? Well, unfortunately, usually you have to draw upon theory mostly. However, if you have lots of counterintuitive results, then this might be the consequence of omitted variable bias. And you just correct it by including the left out variable or in maybe a proxy, or maybe playing around with different combinations of variables. That's why we often use different models with various combinations of variables. A second common problem is the use of irrelevant variables. So this means the inclusion of a variable that does not belong in that equation. Consequences of this are that you have decreased precision in the form of higher standard errors and lower t-scores. Again, theory is behind our detection. You can also run t-tests, as well as look at the r-squared values compared with other models, and look across models at whether when dropping a certain variable, it has a notable impact on the coefficients of the remaining variables. Again, you might just want to delete that variable if its inclusion is not required by the underlying theory. A third problem is something we touched upon with one of the key assumptions, i.e. that the functional form is incorrect. Now you can imagine that if your variable is an exponential curve, but you're representing it as a linear curve, that's going to really mess up your analysis. And it can create biased and inconsistent estimates, as well as a poor fit and problematic interpretation. And so you really need to examine the theory carefully and think about the relationship between X and Y, and whether that variable might have some kind of exponential or logarithmic or U-shaped curve to it. If it may be nonlinear, then contact me and we can think more deeply about how that might look. And you correct that by applying a mathematical function within the equation so that it can be transformed to the appropriate functional form. So fourth problem is one that we touched upon in the assumptions, that of multicollinearity, i.e. that some of the independent variables are imperfectly correlated. So the consequences here are not as dire. The beta values, the coefficients, are not biased, but the estimates of the separate effects of the variables are not reliable. It's very tricky to detect. There's no universally accepted rule or test. Often we look firstly at that correlation matrix, and then we can use a t-test in some ways, or maybe use what's called a VIF test. Now the correction here is relatively straightforward. We might drop the redundant variables, i.e. one of those two independent variables that may be correlated with one another. However, if you drop a variable inappropriately, that may also introduce bias, per our last slide. What you could do is combine the two variables, or maybe just do nothing. Fifth problem is zero correlation. We discussed that, where the observations of the error term are correlated with one another. This doesn't bias the coefficients, but the variances of the coefficients do increase, and therefore the t-scores fall in a way that's not captured by OLS. And for this, you can use the Durbin-Watson test. This is usually an option in SPSS. If it's significantly less than 2, then that would suggest that positive zero correlation exists. Now, if you identify this, maybe you could add that time variable that I mentioned, or you could maybe play around with the functional form. There's also other non-OLS approaches that you could use to try and address this. The final problem, which is quite common, is that of heteroscedasticity, which we discussed earlier. And the consequences for this are the same as serial correlation. So here what we would do is plot the residuals or the error term values to try and detect heteroscedasticity. There's also some tests that you can probably select quite straightforwardly in SPSS called PARC or White tests. There's many more. And if you identify this, then you might want to add an omitted variable. Also, there's other approaches than OLS that you can use, for example, weighted least squares. So as I said, that was rather technical, but I hope it gives you a sense of the complexity of the statistics and the concepts behind multivariate regression. Thankfully for you, for the most part, SPSS can take care of this. And I hope that this can give you an insight into what you might do if you find some of those issues, or if maybe I point them out to you. Either way, please just let me know if you have any questions or concerns on any of these matters.